John Lava Group from University of California, Irvine, talk of numerical simulation of endocytosis.
Okay, thanks, and thanks very much to the organizers for inviting me. And I want to acknowledge at the beginning my collaborator, so Sebastian Hollande, who's a postdoc who's been visiting UC Irvine for the past year. So he's from Axel Volk's group in Dresden. And a new faculty, we hired June Allard, who's joint between math and physics at Irvine. And so the question we're going to address is basically how endocytosis, or essentially the formation of a bud eventually to pinch off into a closed vesicle, can occur, and how it's driven by molecules that can coat the membrane and induce a curvature and bending stiffness. And so, but we want to do this in a fluid, and we were motivated by some recent experiments that were done on synapses to show that basically by stimulating basically the synapse, they stimulate it with light over here, that creates vesicles that actually exocytose, so they give the interface some extra length. Those travel along, and then it leads to endocytosis, which is basically the formation of these buds off the inner membrane here, to eventually form these closed vesicles, which are closed biomembranes. And this occurs very fast, on the order of milliseconds. And so when something like this is occurring quickly, then one can ask how important the hydrodynamics should be important. And so let's try to understand how it limits or enhances the process. And basically, this is a central process for cells interacting with their environment, because the endocytosis is bringing stuff from the outside in to the cell. And so what we want to do is use this, and we'll look at a basic problem. And there's many additional things that one has to do to kind of tackle this experiment, but this is our motivation, and I'll show you our way onwards and what we've learned about this. So the question is now, how can you model a membrane in a fluid with basically curvature-inducing molecules? And so I'm going to do this essentially in two parts. So first I'm going to talk about how you model biomembranes in a fluid in the first place, and we'll use diffuse interface or phase field methods for doing that. And then we'll say, okay, now what do you do to add the molecules, and then I'll show you some results. And so basically, to give the picture, a closed biomembrane like this guy, so the membrane is gamma, you have the inner fluid and outer fluid. The interface is a lipid bilayer, and basically these guys, you can assume they're liquid-like, but they have bending stiffness, and so if the interface isn't changing topology, then you can pretty much use just the normal bending stiffness. You can ignore the Gaussian, since that won't change. And H is the you can either talk about total curvature or mean curvature, just rescales the bending stiffness. And H0 is a preferred curvature. Now, one of the key things that we have to address, and I'll show you the importance of this constraint, is that lipids generally resist compression. So you can't compress them, and you can't extend them. And so what that really means is the surface divergence of the velocity is 0 on the interface. You can't stretch or compress the interface. And so in the first part of our talk is trying to figure out how you can do that. So that's tangential information, how you can do that in a phase field or diffuse interface model, which is typically not doing anything tangential. You're mostly dealing with normal. But so one of the first ways of dealing with this problem would be to say, well, let's ignore local inextensibility and only implement global, so that we don't want the area, or the area of the interface, or the length of the interface as you're in 2D, doesn't change in time. And so these are basically the Navier-Stokes equations written in distribution form. And so that energy is this is exactly this guy, the bending energy. And so the one of the ways of writing the equation would be, well, that energy will induce a force, and that's basically giving you a jump in the normal stress. So you can write it like this in distribution form. And the interface moves with the fluid is incompressible. And then if you want to enforce a global area constraint so that the area of the interface doesn't change in time, you can do that through a surface tension-like term where this guy is a Lagrange multiplier that's being determined to satisfy this constraint. And this variational derivative takes this form, assuming b is constant. And one of the things, so I've included inertia here, and inertia can be important if your flow is sufficiently fast, for example, in large blood vessels, and or if they get constricted, so you have high shear. Now you could say, well, let's, so that's the first formulation. The second would be, and that was sharp interface. The second would be now, let's try to enforce local inextensibility. And so the way you do that is everything is the same, except now instead of using a constant surface tension-like term, you introduce a variable surface tension term, lambda. And this is like a tension on the interface that's being determined to ensure that the interface doesn't change length. And so this guy, if you work out what that is, so this again, delta gamma, I forgot to say in the previous slide, that's a surface delta function. And so you can take the divergence of this, and this just looks like typical Marangoni force. But the key is to determine lambda, and lambda now is determined again by this constraint. P is this tangential projection operator, and so then the constraint is just again divergence, surface divergence of velocity is 0 on the interface. And so now the key is, so this is a sharp interface formulation, and you can implement this in a variety of ways. If you're really trying to account for inertia, then one has to be a bit more careful. If you were just doing the Stokes problem, you could use boundary integrals to do this. So what we're going to do, we want to have it general, so we want to be able to allow inertia. We want to be able to easily go to 3D. And so what we're going to do in principle, if we're looking at endocytosis, then we also want to allow topology changes. And so what we're going to use then is a diffuse interface or phase field model. So I don't have to say too much, at least in the way of motivation here, because there have been lots of talks on phase field models. But so essentially you have a phase field function phi that denotes one of the domains. And then one can write down the bending energy now in terms of the of this phase field function phi, and it takes this form. So this is, you can use a variety of forms, and this is one that Chang-Du and his co-workers came up with. And then the interface, of course, is just the level set of phi, and you can show that this converges to the usual bending energy. And so now what was done with this diffuse interface model previously was basically to include global constraints. So the equation, again, takes the same form, except now your surface delta function, essentially times the normal, is this grad phi. And then if you're introducing global constraints, so you ask that the volume is enclosed is unchanging, and the surface area, total surface area, doesn't change, then you get these two constraint equations, and you have these two Lagrange multipliers that are introduced to determine to satisfy these constraints. Now, of course, so what was done is that this equation is then, of course, you have to couple with an equation for phi, and that's done in using a kind of generalized Willmore type flow where phi is advected, but then you have this nonlinear diffusion-like term. and the constraints enter this, so this has a non-increasing energy, the whole system. And one could use a conservative form, so this is an Allen-Kahn type or non-conservative form, but you could also introduce a conservative form by putting a Laplacian. And so, of course, just like the sharp interface model, this guy will conserve the total area, but you can still allow stretching and compression. Now, how do you add the local constraint? So now let's ask, how can we extend this model so that we can deal with local constraint rather than the global constraint? And so now the key is here. So at no extra cost, we can keep the global constraints, but now we want to add an extra piece that introduces the local constraint. So if you recall about the sharp interface version, well, what did we add in the sharp interface version? Well, we added a surface delta function here, the tangential projection, and the lambda, the tension. And so here we do the same, except now the delta function can be represented as mod grad phi, so that's an approximate delta function. And then, well, what did we have on the surface? Well, on the surface, we had this tensor product between the tangential projection and grad u equals 0, but that was on the surface in the sharp interface. So now what we have to do in the diffuse interface is we have to extend that off the interface. And so one way of doing it is to say, well, you could multiply this quantity by the surface delta function, right, and ask that that's 0. But if it's 0, you could divide by the surface delta function, right, and it would force this everywhere, and that's not what you want. So what we did is we added a regularization. So we add a piece here in this equation that that essentially extends lambda off in a smooth way. So here the convention is that the interface, I did it kind of quickly, the interface is the phi equals 0 set. So on the interface, this guy's gone, and you just have this constraint. Away from the interface, well, phi is constant, it's -1 or 1, so this guy's gone, and you're left with Laplacian. And so what this really is a harmonic extension of lambda off the interface. It turns out that has some pretty nice properties. Well, one nice property, which I'll show you in a second. But this now also is convenient because now we've introduced lambda in this equation, and one can solve this. You can solve this together. The lambda's here, the lambda's here. So now you have a full system you can solve. And then this equation is takes the same form. I didn't say it. The b tilde is related to the b through a scaling constant that comes from the sharp interface limit. And so you can show, if you do matched asymptotics, that this simply converges to the right equation on the interface, and that this extra force converges to the right sharp interface force. Now, let me say about the properties of this kind of harmonic extension. So if you define the total energy like this, so you have the diffuse interface bending energy, and then you have the kinetic energy, because we're still considering inertia. Then you take the time derivative. Well, everything works as one would expect. You get this negative term coming from this Allen-Kahn-Willmore type equation. You have viscous dissipation. And then here is the Lagrange multiplier for the local inextensibility. And so you can, if you integrate by parts on this term, you get a grad u tensor product p, dropping the boundary integral. And then if you use this equation and you integrate by parts again, you get this term. So in fact, that harmonic extension is stabilizing. So it also contributes to energy dissipation. And it's scaled with this epsilon squared, so as you're doing the sharp interface limit, this guy will go away. And so you'll be left with the right thing. This guy will also go away, so you get the go away in the right way, and so you get viscous dissipation. But so this is an added benefit of adding that regularization, is that it gives an additional level of stability. Okay, but now so that's a way of enforcing local inextensibility in a diffuse interface model. But in fact, what can happen is that if you start to make errors in the enforcement of that constraint, those errors can accumulate. And so even though you think you're satisfying the equation, well, you always have discretization error, and so the question is, how does that accumulate and affect the result? So it turns out, of course, it can, and that's well known. It's well known that if you have small errors you want to compute for a long time, they will accumulate. So what we did to try to get rid of accumulation is to introduce a relaxation. So every time the system tries by numerical error essentially deviates from being inextensible, we wanted to introduce a force to push it back. And so one can do that in a kind of straightforward way like this. So what you really want to do is measure the amount of local stretching. Well, you could measure the amount of local stretching by doing the surface divergence of U, but there's another convenient way to do it, which is simply to do a surface conservation equation, and track that surface concentration. And so, in particular, if you started with 1, a surface concentration 1 on the interface, and you're exactly conserving it, then if it deviates from 1, if it's bigger than 1, it means you compressed, and if it's less than 1, you expanded. And so then what you can do is you can introduce a Hooke's law force. So what you can say is that now what you do is that this is the surface divergence of U, and so if C is bigger than 1, you've compressed, so this should drive an expansion force. And if C is less than 1, it's expanded, so you introduce a compression force. And so then what you can do, so you can introduce this, and there's a relaxation rate zeta. And so you can do this in the sharp interface version, or you can do this in the diffuse interface version. And so instead of putting 0 here, you can put this term, and what this term will do is that this will drive you back to the inextensible configuration. Because in the model before, there's nothing to guarantee. If you deviate a little bit, there's nothing to push you back. And so we call this model C. And so actually when we solve this equation, this surface conservation equation, the way we do is we add a little bit of diffusion to stabilize the method. But this diffusion can be made quite small. And so, but I have another equation I have to solve. And so this is a surface conservation equation. And you can implement this. So again, this was written on the surface, but you can implement this using a diffuse domain approach, where essentially you put delta functions in the right place, and then you solve the system instead of with surface gradients, but with full gradients. And essentially you only need to solve this near the interface. But it turned out, so this was the original method that Andreas Rautz and Axel Voigt came up with, but it turned out that actually to do this, there are constraints on how big you can make this in their original method. It turns out if you introduce a normal diffusion, that acts to, in this diffuse interface framework, one of the conditions for this guy being a good approximation is that the field needs to be extended constant in the normal direction. So it turns out that if you introduce a diffusivity in the normal direction, in addition to the tangential direction, then this method is much more stable, and it allows you to take this guy much smaller. Okay, and so you can show that for this revised system, just like this one, you converge to the correct sharp interface limit, and by doing it this way, you're exactly conservative even on the discrete level. Okay, so we have 3 models now. So we have what we call model A, which is the model of do and all. where you introduce the global constraints together with the Willmore advection. Then we have model B, which introduces local inextensibility by this Lagrange multiplier and this modified surface equation. And then there's model C, where now you introduce the relaxation, and now you have an additional equation that you have to solve to measure the stretching on the interface. And so now what we do, Sebastian is an expert in finite elements, so we use the code that, or at least the package that the Axel and those guys have developed. And so one of the key things is removing the stiffness. And so so where does the stiffness come? The stiffness comes from this piece, because this guy is involving fourth derivatives, right? And it's in the fourth. And so this guy causes the stiffness. And basically, you would have to have the time step less than the space step to the fourth power, so that's very restrictive. And it's not easy to do because this guy's coupled with this guy through only the fluid. But it turns out that if you do this guy implicitly, this piece explicit, one can get something like an energy stable method that ends up having, you're able to use much larger time steps than you could if you were using an explicit method. So it gets rid of very strong time step restriction. Okay, so now what we're going to do is we're going to test the model, and we're going to do it in a couple of configurations. Well, mainly to test the model and just to show you that it's working, I'll look at a vesicle and shear flow. So this is an experimental result where for high shear rates, the vesicle tumbles. If you reduce the shear rate a bit, the vesicle trembles. And if you reduce it even further, and so trembling just means that this long axis doesn't go around. And if the shear rate is sufficiently low, it tank treads. So here's tumbling, you see it rotating. And then tank treading, it's roughly stationary. And then trembling, this long axis doesn't rotate around.
That's a 3D simulation.
That was an experiment.
Oh, that's the experiment.
That's the experiment. So this is a 2D simulation. And so the Reynolds number is small, so this is pretty much Stokes flow. And so this is 1 over this is the bending stiffness, and there's no spontaneous curvature, and there's a viscosity ratio. It's 10 inside, 1 outside. And so what you can see is that the vesicle is tumbling and rotating around. And one of the things that then we want to use this is we want to test what's the effect of inextensibility. And so you can measure inextensibility in 2 ways. Well, at least 2. So one is measuring what we call the instantaneous stretching. So you take the surface divergence of U and you integrate it over the interface in, of course, the diffuse interface framework. And then we ask how this behaves as you reduce the interface thickness. Because we did introduce a regularization that depended on the interface thickness. And so what you can see is that this is the error, so that's this guy, as a function of epsilon. This is first order convergence in epsilon, this is second order, and so it's somewhere in between. But certainly it's going down to 0 as you decrease. And this is for model B, the one where we introduce local inextensibility, but not relaxation. Another thing you can do is you can measure the accumulated stretching. So by looking at the accumulated stretching, you're basically seeing the deviation of C from 1. And so that's taking everything into account that occurs up to the time you're measuring the error. And so here's this error as a function of epsilon for the case where you don't include relaxation, so model B, and the case where you do. Again, you see this convergence to 0. That's roughly between first and second order in epsilon. And Model C starts maybe a little bit larger, but as you reduce the epsilon, it's smaller, the accumulated. And this is only short time result. I'll show you. So this is measuring the error at a relatively short time. If you then say, now, let's compare the time evolution of the vesicles. So this is the global constraint. These two are local. This is no relaxation. This is with relaxation. So the global constraint just lets this guy rotate. The local, with no relaxation, lets it rotate, but more slowly. And this lets it rotate, but even more slowly. So it has a non-trivial effect on the dynamics. And now what you can do is you can say, well, let's measure the local stretching. So we'll pick a time, and this is the time. So this is a relatively good time to look, because this is when it's nearly steady before it tumbles. And so the interface is being colored by the surface concentration C. Okay? So the C should be 1. And what you see is that for where you have the global constraint, model A, the interface is compressed. So C is around 1.5 at the tips, and it's maybe about 0.7 along the side. So you have significant, even though the global area is surface area is being conserved, locally you have a lot of stretching and compression. In model B, well, now you look at the range, it's much smaller, 0.95 to 1.038. So you still see red and blue, but the scale is much smaller. But nevertheless, you do see stretching. And if you look at model C, now you're quite close to an extensible. And now what you can do is you can then look at the accumulated stretching, but now over a longer time. And so what you see, this is the accumulated stretching as a function of time for the 3 models. This is the case with the global constraint. So you see this guy is just wandering away. This is with the global constraint, the green, but no relaxation. And so what happens is these peaks are associated with tumbling event, because when it tumbles, its shape changes quite a bit. And so it's very hard for it to maintain inextensibility. And so this peak is associated with the tumbling event. This peak is associated with the tumbling event. And so once you've done that, then this just kind of wanders away. And then this rise is associated with tumbling, but it gets damped right back by the relaxation. And this is just looking at the inclination angles for the different cases. And so the red is model A, so it has a bunch of peaks because in this time interval it tumbles twice. The green also tumbles twice, but the blue only tumbles once. And now if you, so this is for Reynolds number 1/200. And if you instead do Reynolds number 1, you again look at this inclination angle. So that's the angle between the long axis of the vesicle and the x-axis. I should have said that before. And now if you do Reynolds number 1, well, you don't see any jumps, because what happens is the system just tanks treads. It doesn't tumble. So it maintains a steady shape. So inertia suppresses tumbling, and that was known. And so at least we're consistent. Now, one can also include thermal fluctuations. And so here's a case where, so this is now, again, 2D simulation, but now this is at least closer to the experiment, because one can include thermal fluctuations essentially by introducing a random stress tensor with the right covariance. So the thermal fluctuations are put in the fluid, not in the interface. Just like you do that to satisfy the fluctuation dissipation theorem. And here what we've done is we've changed the, rather than changing the shear rate, we changed the viscosity ratio, and that's another parameter that one can use to change the, do the transition. So this guy will tank tread, this guy trembles, because you can see this is the, this guy never crosses the axis, and this guy tumbles. And this is, again, consistent. One can do phase diagram, and this lies in the right region for experiments. But this is a 2D simulation. Now, here's an interesting case, and this is probably the most interesting case that when we'll come to the actual endocytosis. So this is all build up to get there. So here what we do is if you now take two vesicles and you drive them together with a shear flow, so, with an extensional flow. So we're pulling fluid out here and pushing these guys here, so we're driving them together. And so if you use model A, so that's the global constraint, well, what happens is that these guys get close, the diffuse interface takes over and pinches it off. So some type of model of van der Waals forces. But if you use the locally inextensible versions, in this case, both B and C give you the same result, so whether you do the relaxation or not, what happens, you drive them together, but then you can't squeeze the fluid out. And you can't squeeze the fluid out because the interface is inextensible. You would have to stretch it to get the fluid out. And so this is really quite at least to us, it was quite a non-trivial example we didn't realize before. We should have, but we didn't, of the effect of local inextensibility. Okay, so now that's all model development to get the pieces together. Now let's introduce the membrane, the curvature-inducing membrane molecule. So we're going to use a continuum formulation. And so essentially what we're going to do is use a surface concentration. And one could interpret the surface concentration in a bunch of different ways, so at least two. One is that it's really a concentration. So if you had small molecules, then it's really the number per unit area. Or if you had big molecules, then you could imagine that the surface concentration might be 1 or 0. You might not be able to put anymore. So in some sense, you could use something like a Cahn-Hilliard equation. So we want it to be conservative. So you would use a Cahn-Hilliard equation on the surface. Or you could just use a diffusion equation on the surface, depending on how you interpret the S. And so we're thinking of doing big molecules, so we can use, for the results I'll show, we'll use a surface Cahn-Hilliard equation to describe this guy. So essentially keeping 1 or 0, but allowing it to move around. And so now what one can do then is, again, modify the energy. And so if you, this is just in the sharp interface version, you modify the energy through the bending stiffness, because these molecules are quite stiff, so they change the bending stiffness, and they also have a curvature, so they change the preferred curvature when they're attached. And you can do different choices for these guys, and the one I'll show you the simulation for is just linear interpolation. So we're assuming that where you don't have the molecules, the spontaneous curvature is 0, and the bending goes to whatever the membrane bending stiffness is. But you can also do local coarse graining and get more complicated formulas. Okay, and so now what you can do is, again, you can go through the same formalism to try to derive the equation. And so you can do it as basically using variational calculus to try to figure out, well, what's the singular force? So here I'm writing actually as through a jump. So what the jump in normal stress should be a singular force. This is the local inextensibility effect, so the variable tension on the interface. And then to be consistent, you see that you get this force, and this gives you this decreasing energy. And so essentially what we had before was this piece, and then this is the new piece. Over here. And so that gives you a sharp interface version of this guy, and so then you can also do the diffuse interface version, or the phase field version. So you extend in the usual way. You use the phase field form, but now your spontaneous curvature is a function of the S, and the B is a function of the S. And if you assume that S is just advected along the interface, and so why is that? That would be because you have local inextensibility, just assuming that's true. then you can figure out the F by doing the energy balance. And the F is exactly what you would expect, the variational derivative with respect to phi. So this is the term we had before. And then it's the derivative with respect to the curvature molecule S, so with grad S. So this introduces additional force in the fluid. And then, and so that guy is exactly, I think I wrote it down here, the EDS somewhere. It's just the derivative with respect to, there, it's this guy. Just derivative with respect to S. Okay, and so now what you do is, well, this is the extra piece you have to add. You have to put this guy in, and then this guy gets modified because the bending stiffness now is a function of the molecule, and so it just comes in here. And now, for the model, we instead of using advection, we use this interfacial Cahn-Hilliard equation. And so that takes for the S, because then we're modeling this as either completely covered or not, thinking that you have a large molecule. And so then, well, this is just the standard diffuse interface way to put in the, so mu is the chemical potential. And so this is the standard Cahn-Hilliard piece. We introduce normal derivative to extend mu constant in the normal direction. And then the chemical potential is determined this way in terms of the S variable. And then we are also introducing relaxation. So we're keeping the relaxation because that's the model that worked the best. And so then we also have this equation for C. So now this guy is the diffuse interface model when you include these surface molecules. And again, we use the finite element package with this monolithic solver that removes the stiffness. Okay, so now let me show you some results. So basically, what we're going to do is we're going to start with these will be axisymmetric. So these are 3D axisymmetric symmetry. And so this is the configuration. You're really solving in a cylinder. And we're going to have so now we're really going to try to at least get a little bit closer to the experiment that we were motivated by. And so we have the extracellular fluid, the intracellular fluid, and here's the membrane. And so we now are going to pin the membrane here in the sense that we're going to keep this contact angle 90 degrees. Here just for simplicity, but we're going to allow interface to flow back and forth depending, so we're going to use a free stress condition. We're going to allow interface to flow back and forth, thinking that there's some kind of reservoir out far away that will allow the interface to increase its length if it needs to. And then we use some realistic parameters. And so essentially what we do is we cover the interface with a region with this molecule, and then we let it go. And so, and then what we're going to do is we're going to vary the amount of coverage. So we're essentially, because we're doing 1 and 0, so this is the region with the molecule on it. To test the effect of the coverage, we're going to increase the size of the spot. So the first thing is, maybe it's a little hard to see, but so this it induces a positive curvature, and but if the spot is not very big, it won't really form a neck, and will just create kind of a bud. Now, if we increase it a bit, then what happens is that there's enough positive curvature, and now it starts to neck. But it doesn't neck off. The simulation's actually still running. I mean, it's done at home, but it's still running. It doesn't pinch off. And the reason it doesn't pinch off is because it's inextensible. It can't get the fluid out of the neck. And that's actually physical, because biologically it's known that actually that it's not enough to just have this surface molecule, so the classic one is called clathrin. It's not enough to form a vesicle if you just have clathrin around. You need something else, and that something else, well, can be a bunch of different things, but one is dynamin. And if you don't have this, these guys don't pinch off. And so that's what the model is predicting. So this is just over time what happens to that simulation I just showed. This is the slice now of that 3D simulation, and you basically get no flow in the neck because it's inextensible. If you didn't have the fluid, and you just solve the Willmore problem with the but with the surface molecule, and so you're just solving essentially the Willmore equation, but driven by the energy with the different bending stiffness and different spontaneous curvature, it would happily pinch off. Okay, and so that's curious and an important effect of inextensibility that we didn't appreciate at the time, at least as we started to do it. So now what you can do is you can say, well, let's see what happens as we vary the amount. So I just showed you two cases, so this one and this one. But you can likewise just increase the coverage or the size of the initial spot of the surface molecule. And you can ask so what you can see is that the morphology depends, and in fact you start to form these mushroom-like shapes if you keep increasing this. But nevertheless, these don't pinch off. And you can say, well, how big is the bud that you form? So here you can't really define a bud. So this is kind of the limit of where you start to define a neck and a bud. And so while that happily increases linearly, but if you look at the radius, what you can see is that as you start to increase this coverage, you see a minimum. And so there's a relatively steep decrease as you increase the coverage to going to this minimum. But then it starts to increase again, and that's because of this negative curvature that forms up here. So there's a minimum, and so you could think, well, if there's a minimum in the neck radius, maybe there's a minimum time to form the neck. And so then, indeed, if you plot the time to bud, essentially when it stops changing, as a function of the vesicle diameter, then you again see this minimum. So you see this minimum. So that predicts that there's a certain amount you need to get it to go the fastest. And the numbers are kind of in, at least the vesicle diameters are in the right ballpark for the experiment. What we're not modeling in the experiment, and that's the next piece, is is how you get the molecule to the interface. We've started with it on the interface, but a limiting factor. So we showed that if it's on the interface, you actually, converting to physical units, you get microsecond budding. They're millisecond. But they have, in the experiments, of course, those molecules have to get there, so they have to attach. And so that's the next piece we're going to add, is the surface bulk coupling. So we have the methods to do it, it's just a matter of now that's the next thing to do. And so to summarize, basically what we did is we had to develop a method for dealing with local inextensibility in a diffuse interface context. So again, how are you converting surface information, so information along the surface, into a phase field method, which usually only accounts for normal variations. And so we did that by essentially modifying extending introducing the Lagrange multiplier, extending it off the interface using this harmonic extension, which has some at least nice energy properties. It decreases the energy also, so it's additionally stabilizing. And so and then we tested it and showed the effects of the constraints and the interesting effect of local inextensibility. And so now I showed you a case with thermal fluctuations. You can also use this framework for other cases. So this is a kind of model of near contact of cells, and one of the interesting questions here is how close do these membranes actually get before you get binding. So one can use this model to try to investigate that as well. And then for endocytosis, basically, well, we derived the equation, but the inextensibility prevents pinch-off, so we have to introduce, so additional things one should do with the model is now introduce this extra force to pinch it off that's coming from this extra molecule, this dynamine, that has to be around. And then we want to do the surface bulk exchange, and this could be, so the transport and could be the limiting factor, and that's what the biologists tend to think, is that it's the slower process of getting the molecules to the interface. Once they get there, they don't unbind, but getting them there and getting them binding may be a rate-limiting step. And and seeing how so there's an interesting question there, because the molecules have a curvature, and so the binding rate should depend on the curvature of the interface. And so that's an interesting coupling between the surface bulk exchange, where the rates actually depend on the geometry, not just a given rate. So with that, let me stop and take any question.
A very nice talk, John.
Thanks.
I have two questions, related to, one is about the last one, is a pinch-off. It's strange that without fluid, it actually pinches off geometric effect, and then with fluid, it does not.
Right.
So I noticed you already added the fluctuations in the fluid, in the stress. But there are two kinds of fluctuations. You probably know that. One is the interfacial fluctuation. So I don't know if you have tried the.
That's not. So if you do that in these types of models, you do not. That's not satisfying the fluctuation dissipation theorem. You can't add adding the noise or the fluctuations to the membrane equation is not the right thing to do.
No.
The right thing to do is to do it in the fluid, and then the membrane inherits those from the fluid.
But it's possible to add it in the speed equation, like
I know, but that's wrong physically.
like Walter did with karma.
Yeah, but it's not correct.
So you don't think that?
No, what you're in order to satisfy the fluctuation dissipation principle, you have to put it in the fluid. You don't put it in the equation for the membrane. You put it in the fluid, and then the membrane inherits that. I know there are models out there that do that, but they're not. I don't think it's correct.
It should be linearized version. Sometimes for nonlinear equations, the fluctuation dissipation is very difficult.
Right, and so of course I'm saying that, and for all the results that I know, including fluctuations, they can justify that in the case when they're doing Stokes or unsteady Stokes. So here we're doing Navier-Stokes.
Oh, okay, maybe that.
But still, I still think the right thing to do is put the fluctuations in the fluid, but not in the membrane equation. You could do that, but I don't think it's the right thing to do.
The other one is about this dynamine molecules. I don't know about this molecules that like hydrophobic, because if hydrophobic molecules come in and it will exclude water molecules away, so that will help pinch off.
Right. So I don't know the mechanism by which the dynamine's working. So that might be one, or it could somehow be there and constrict the neck as well. So I don't know. That's a good question.
So
Yeah.
this neck formation and disappearance is a very quick process.
So what the simulations are predicting is that if you get the molecule on the interface, then forming this bud and neck is a quick process, quicker than what they would observe biologically. And so that's suggesting that the rate limiting step is getting them there. But and getting them there is non-trivial, because the binding rate should depend on the geometry, the interface geometry. Yeah.
How many molecules would there be?
So that's a good question.
I mean, create the.
This thing. I don't know the answer to that. They in our cartoon they code it,
Yeah.
but exactly I don't know. And also it's not clear in their. Oh, I think I have to put my passport in. It's not clear in the experiment which is the molecule. So is it a big molecule? Is it small? Is it even that molecule? Is it even a molecule? So they were actually claiming it's maybe not clathrin, this large molecule. Maybe it's small molecules or something else. But those are good questions. I don't know the answer. How many they really are. Yeah.
Related question: What patterns the clathrin? Why is it in a little region? And
Yeah. So that was our modeling choice, and just to get a start on it. But really, in fact, what should happen is that you should have a nucleation point somewhere, something is attaching, and then you have to have this, because the molecule is not on the interface originally, so it has to attach from the bulk. And then that process of how it's attaching may, here it was highly idealized, but it may not be, looking like this. You might have, in principle you could have different spots, but maybe they somehow prefer to be aligned, linked together as they come on. But that was just a modeling choice, why it looks like that. So we didn't vary that also, so that's another thing one could vary. The shape, what that is. Another one? Yeah.
Comment really. There's some interesting numerical questions associated with solving these equations.
Yes.
Really quite hard numerical analysis questions.
Absolutely. So
So
hopefully you'll be motivated to to think about them.
It's not that easy to get these computations to really accurately approximate the sharp equations.
Right. So one big piece that we hadn't realized before doing this was actually adding the diffusion in the normal direction for the surface field, and that helps a lot.
So there's some interesting numerical analysis
Yes.
around that. I can point you to.
Okay, so that would be great. So did you guys include the?
Well,
I know that you've done.
In the diffuse interface. We had this kind of like a cross streamline diffusion.
Oh, okay.
And
So
it's a bit like that.
okay.
Artificial diffusion. But actually, if you don't solve with divergence phi squared grad lambda, for example, because you use this all the way through. If you solve with the full Laplacian, you get a penalty in a normal direction.
Okay.
That's
Okay, so that's also interesting. Yeah, because we just made one choice of the surface delta function. You could use any combination of choices. Yeah. Yeah.
Another science speaker again.